define something called the dew point. This is the temperature where the water cannot stay in the air anymore, and it will end up basically dropping as water droplets on cold surfaces, like that what we see in the morning in the on the lawn. You know, when you if you are leaving your home early and you look at your lawn and it's like all water, and like, did I turn on the sprinkler? No, you didn't. It was too cold, the water and humid, and the humidity in the air end up condensing in the cold grass plates. Okay, so what when this happen and what temperature? Because he will ask you to calculate that temperature. What temperature does it take to make the water drop from the air? So here is the air sitting at the initial temperature, whatever that temperature was, and his vapor pressure. And so let me ask you, is that 100% humid or not? No, it's not, right? If he was 100% humid at that temperature, where would he be? He would end up being here, right? In this place. But he's sitting here. So his relative humidity is, you know, 50%, 60%. He's sitting over here, not 100%. All right, at that temperature and this vapor pressure, right? So now what happens if the air and the water vapor, because we said all of them are sitting at the same temperature, right? They have different pressure, partial pressure, but they are all sitting at the same temperature. What happens if that temperature is cold? You know, it's getting dark at night and the sun is not there, and the air start to get cooler and cooler, and the water vapor in the air getting cooler. So that line will drop, right? So instead of sitting here, the temperature would be here. But as the air and the water vapor are dropping in temperature from this place to this place, will the vapor pressure change or not? So what is the vapor pressure? It's mole fraction, right? For the same B atmosphere, same constant mixture. That's what he's saying over here. For the same constant mixture pressure. So we are all at 1 bar or 101,325, whatever the atmospheric pressure is. We are all sitting at the same same total pressure, right? Same mixture pressure. So as we take that temperature of the air and the water vapor to a little bit cooler temperature, will the vapor pressure change? Or basically, will the partial pressure change? It will not, the partial pressure of the water vapor will not change because the mole fraction didn't change. We didn't add water, we didn't take water. And so he's sitting at the same mole fraction, and therefore at the same vapor pressure, right? So what I'm saying is that if we start here and we take everything to lower temperature, we will end up basically intersecting here. The water vapor will be sitting at this place now. Lower temperature, but the same vapor pressure. And you can see what will happen, you expect, right? So what will happen next is we will drop until we meet this point. That is point D. So he's saying if you take the air and the water vapor to as low as this point, now the water vapor will, same partial pressure, will find itself sitting at 100% humidity, right? Relative humidity, right? Because here at this temperature, if he is at the temperature and that vapor pressure, his vapor pressure now is the saturation pressure. You manage to cool it down to become 100% humid air. Now it goes on down even more. So 3 o'clock in the morning, 4 o'clock in the morning, and it's really cold. Not just 100%, not just at this temperature, but it will drop all the way to this temperature. And now as we drop to that temperature, the water vapor will be, he will have to be condensed he will have to be sitting at saturation pressure, right? Sorry, saturation temperature. So he will end up sitting here at saturation temperature and saturation pressure. The water vapor will be sitting here, and as you can tell, because that pressure is way higher than this, the final pressure is lower, right? Because he needs to sit at that temperature. So what does it mean that he's sitting at lower pressure than the initial pressure? Whatever mole fraction that caused that partial pressure, now he have to have a lower mole fraction. Okay, lower mole fraction mean less number of molecules of the water vapor in the air. So if he is sitting at this temperature and that pressure, that means that he will have lower mole fraction, and that means that a little bit of the water vapor molecule are no longer with us. They are water molecule, liquid water, not uh, vapor, but instead liquid. And they will be sitting on the grass, on whatever cold surface is. All right. So also windows, like I love one thing about my bathroom is that our jacuzzi basically is having windows in front of it, so that you are sitting in jacuzzi and you are basically looking at the backyard. But because the restroom is humid, because people take showers, and the windows get very cold at night, then you always see water vapor condensing at the windows of the restroom. And then those water vapor condense at the surface, and then they drop. And so you go up in the morning and you see all this water film basically dripping from the windows into the wooden frame of the window in the restroom. So it's horrible actually. So I mean, you enjoy the view, but then you get all this water film condensing on the window. So that will happen when the window's temperature is as low as, less than this, right? If you take the windows and you go lower than this, then the water will start condensing at the window, right? How much water will actually become liquid? Well, calculate the difference between this and this mass and this mass, and the difference between them would end up being water liquid. And they will actually ask you about this. They will tell you in some problem, well, can we calculate how many what's the mass of the water that condensed? Okay, by this formula. So how many molecule, or like what is the kilogram of water that condensed? Well, calculate what did you had initially, the mass over here, and calculate what is the mass over there. Okay, initial mass minus mass. And so to calculate that difference between 1 and 2, omega 1 and omega 2, that is how much water condensed. And you notice that he divided the whole thing by dry air, which didn't change in the whole process. The air mass didn't change, right? So that become omega 1 and that become omega 2, and that become how much water did we condense per unit mass of dry air. To get the initial omega 1 and the final omega 2, we have this formula that basically say B vapor and the total pressure, and over here it's B gas 2. Why B gas 2? Because he's saturated, right? At 2 he become saturated, so it's PG, right? Very good.